Hi, this is Dr. O'Connor. Welcome to Pathways to Chemistry. And today we're going to look at an initial rate law problem. And you've done many of these in class, but this one is a little different. And they're asking us to determine the rate law, the rate constant, and the initial rate of triiodide ion formation. And we're given reactant concentrations for that. So how this problem differs, we have 3 experiments. Now notice in experiments 1 and 2 for the iodide ion, the iodide concentration is held constant. And so we would be able to compare these 2 experiments to determine the exponent m. But for this 1,1-dibromomethane, the concentration is not held constant. But never fear, we can still determine the rate law and the rate constant from this data. So I'm going to show you how to do that. So let's see, I think I forgot to write the equation here, so I'm going to do that. So the equation is C2H4Br2 plus 3 iodides and we have 2 bromides and 1 triiodide ion. So I would write the rate law. I better write it down here. I would write the rate law as rate equal to K and we have the concentrations of the reactants here, and we'll make this to the m power. Remember, these exponents can only be found through experiment. And then here we have the iodide ion, and that'd be to the n power. So what we need to do is find both m and n, which correspond to the orders, the order with respect to each of the reactants. So let's go ahead and do that. I'm going to look at experiments 1 and 2. And the reason why is because the concentration of iodide is held constant. So let's go ahead and compare those. So the rate of experiment 2, and I'm going to put experiment 2 in the numerator because the initial rate is larger than the initial rate for experiment 1, and it's the math just turns out it's a little bit easier. Okay, so I'll write the rate for experiment 1, and that'd be K, or for experiment 2, I'm sorry, that would be K. We have 0.686 molar, and that'd be to the m power times 0.204 molar, and that would be to the n power, and that's equal to 3.48 times 10 to the negative 4 molar per second. Now I'll divide that by the rate for experiment 1. So let's divide this. So that would be K and 0.254 again to the m power. This would be 0.204 to the n power, and then that would be equal to 1.29 times 10 to the negative 4 molar per second. Now what's going to happen is the K's cancel, these cancel, and then we go ahead and divide the these concentrations here. And when I divide those, let me find my calculator here. There we go. Let's see. When we divide these, we get 0.686 divided by 0.254, and I get 2.7. So this would be 2.7 to the m power, and that'd be equal to, and we'll go ahead and divide the initial rates here, and I get 2.7. So in this case, 2.7 to the m power is equal to 2.7. M would have to equal 1. All right, so I can go up here then, and I can change that m. Whoops, that didn't work. I think I'm just going to have to rewrite it later. Okay, so we have our m equal to 1. Now, let's go ahead and find the exponent n. So our reaction then is first order in 1,1-dibromomethane. Okay, so I think for the second part, I'm going to compare experiments 2 and 3. So I will compare experiments 2 and 3. Again, the 1,1-dibromomethane is not held constant for any of these experiments. So I'm just going to use this data here in order to determine the exponent. So let's do that. And I'm going to divide experiment 2 by the rate of experiment 3. Again, that's because the initial rate is larger in experiment 2, and it just makes the math a lot easier. Okay, so we're going to look at rate of experiment 2 over rate of experiment 3. And I'll go ahead and write those out. So we have K, and that's going to be 0.686. Now, we already determined the exponent m, so that's just to the first power. And then we have 0.204 to the n power, and that's going to be equal to 3.48 times 10 to the negative 4 molar per second. And I'll go ahead then and divide that. From experiment 3, we have K, and this would be 0.406, and again, that's to the first power. We already determined m, and that'd be 0.25 to the n, and that'd be equal to 2.52 times 10 to the negative 4 molar per second. Okay, so again, this cancels. Now here we'll just take the 0.686 and divide by 0.406, and we get 1.69. So this would be 1.69. And then we divide 0.204 by 0.25, and we get 0.816 to the n power. Okay, so let me put that in parentheses. And then when I divide the rates, I get 3.48 to the negative 4. Whoops, my calculator. Actually, it's the person using the calculator. It's to the negative 4 divided by 2.52 to the negative 4. And I get 1.38. Okay. So what I need to do here is solve for n. So I solve for n, and when I do that, I get, well, what I need to do is divide both sides by 1.69. So 0.816 to the n power is going to be equal to 1.38 divided by 1.69, and that is equal to 0.816. Okay, so now so what we have is 0.816 to the n power is equal to 0.816. N must be equal to 1. So n is equal to 1. So now I can write my rate law, and that takes care of part A in the problem. So my rate then will be equal to K, and I have my 1,1 dibromo ethane, and then my iodide ion concentration. So that is my rate law. Part B asks for the rate constant, so we need K. So I'm going to go ahead and solve for K. So K is going to be equal to the rate, the initial rate, over the concentrations of the reactants. So the 1,1 dibromoethane and the iodide ion. My exponents, again, the order with respect to each reactant is 1, so I don't have to worry about that. And I'm just going to use the data from experiment 1 in order to determine my rate constant. You can use the data from any of the experiments. I'm just choosing experiment 1. So that's 1.29 times 10 to the negative 4 molar per second. And we have 0.254 molar of the 1,1 dibromoethane. And again, the exponents are just equal to 1, so if they weren't, I'd have to include, if I had to the second power, I'd have to include that in this. And this is 0.204 molar. And I get an answer of 2.5 times 10 to the negative 3 per molar per second. Okay? And you have to, we know that this is a second order reaction, and because it's we know that it's second order overall, so our units do correspond to a second order reaction. Okay, so we have that part done. Now in the third part, in fact, I better scroll back up, and let me go ahead and write this down here so I don't have to keep moving the screen. 2.5 times 10 to the negative 3 per molar second. Okay, so we know that our reaction is second order overall and first order with respect to each one of the reactants. Okay, let's go back up here now. They want to know the initial rate of iodide formation when the reactant concentrations are both 0.3 molar. So that's fairly easy to do. All we need to do is determine the initial rate. We can use our rate constant in order to do that, right? And so we know that our rate is equal to K, and that'd be the concentration of the 1,1-dibromoethane and the iodide ion. So I'll go ahead and plug these in. So that's 2.5 times 10 to the negative 3. And we'll go ahead and put the concentrations in. That's said 0.3 molar for both. And our initial rate then at these concentrations is, we have 2.5 to the negative 3 times 10 to the negative 3 times 0.3 times 0.3. And I get 2.2. Now I gotta find my pen. There it is. 2.2 times 10 to the negative 4. And then we have to check our units here. And that's molar per second. Okay. So we can, we know that the rate of disappearance of the 1,1-dibromoethane. Okay. Oops, I forgot my delta here. Sorry, I have to erase this. Okay, so we know that our rate of disappearance of the 1,1-dibromomethane, ethane, I'm sorry, I keep saying methane, is equal to, and we'll take a look at our equation here, the formation of the triiodide ion. Sorry guys, I'm having a little trouble here with my, okay. And let's look at the reaction here. We have a coefficient of 1 here and a coefficient of 1, so this would be correct in representing the initial formation or the formation of the triiodide ion. So this then is equal to, remember the negative sign just shows that it's a rate of disappearance. There's no such thing as a negative rate. So this would be 2.2 times 10 to the negative 4 molar per second, and that would be equal to the rate of formation of the triiodide ion. So that would be 2.2 times 10 to the negative 4 molar per second. So anyway, I hope this helps. You normally in introductory chemistry don't come across this type of problem where the concentration of a reactant is not held constant over 2 experiments or more. So I hope this helps. Everybody have a great day, and thank you for watching.